Hello everyone. Here we are going to prove that a group with two elements of order 2 that commute must have a subgroup of order 4. Okay, so let G be a group. Here we are not assuming anything about the group G. Group G could be finite, infinite, it could be abelian, non-abelian, whatever it is. Okay, group G has at least two elements of order 2. Okay, and these elements they also commute with each other. Okay, there are two conditions that are satisfied. One is that there are two elements, at least two elements of order 2, and then they also must commute with each other. Now okay, now we must show that group G has a subgroup of order 4. Okay, so for this what should we do? Let's begin with the existence of two elements. Okay, so let alpha comma beta be elements of G such that, of course, alpha and beta have to be different, right? Alpha not equal to beta, okay? Because there are at least two different elements of order 2. So alpha not equal to beta, and order of alpha is equal to 2. That means alpha square is equal to identity, and order of beta is also equal to 2. That means beta square is also equal to identity. Okay, now we have to say that it has a subgroup of order 4. So what we will do is we will construct a subgroup. Okay, so for that what will we do? Consider H. Okay, now we are trying to construct a subgroup, right? So definitely identity element we should definitely put it in. Okay, we are considering a subset H of G. Okay, in that we will put some elements from G, and then we will show that it is a subgroup and it is of order 4. Okay, so for that, since it is a subgroup, definitely identity element should be there, right? Okay, now we will put in this alpha, we will also put in beta. All right, now we should also consider their product, right? Alpha beta also should be there. Okay, for the time being we will consider these elements, but then we should also be worried, right? Can we close this? Should there be any other elements? We should we know that H, for H to be a subgroup, it must satisfy closure and stuffs, right? So should we there be any other element? As of now we don't know, so we will just write down the table and then we will check what is happening. Okay, now even before that there must be one another thing. Here we have identity. Alpha is definitely different from identity because order of alpha is 2. Alpha square is 2. Okay, alpha power 1 is not identity. Okay, because order of alpha is 2. Okay, so alpha is different from identity. Alpha is different from beta. Okay, by construction. We know by what is given. Okay, similarly, beta is also different from identity. That much we are sure. But what if alpha beta is equal to identity? Then there is no point in proceeding further, right? So we cannot get a subgroup of order 4 from this. Okay, we are now here we are just trying to construct. Okay, we are just taking some elements and trying to construct a subgroup. Okay, and then if we are putting identity alpha beta, and then if alpha beta is again identity, then we will just get a subgroup of order 3, right? There cannot be much more things. So we need to check what will happen to alpha beta. Will alpha beta be different from identity? Will alpha beta be different from alpha? Will alpha beta be different from beta, and things like that? Okay, first we should check about alpha beta. Okay, so can alpha beta be equal to identity? Okay, suppose alpha beta is equal to identity. Sorry, identity. Okay, then what will happen? Then that implies that beta is equal to alpha inverse, right? Alpha beta is equal to identity will imply that beta is alpha inverse. But we know that alpha is of order 2. That means alpha is self inverse, right? Alpha inverse must be equal to alpha. right? Because we know that identity is equal to alpha square, so we can write this as alpha into alpha. Then we will multiply by alpha inverse on both sides, so we'll have alpha inverse is equal to alpha, right? So alpha must be self inverse, so alpha inverse is equal to alpha. So this will imply that beta has to be equal to alpha inverse, which is equal to alpha. That is, beta is equal to alpha, but this is a contradiction because we are taking different elements alpha and beta, right? We have begun with alpha not equal to beta. So this is not possible. So alpha beta cannot be equal to identity. Okay. Now, can alpha beta be equal to alpha? Let's check. Now we can write alpha is equal to alpha times identity. That is fine, right? Now this I can write it as alpha beta. Now alpha is an element of group G, alpha beta is an element of group G, right? There we have the left cancellation property. So using that we can cancel this alpha. Okay, or in other words we can say that we can imagine like we are operating with alpha inverse on both sides. So this alpha will get cancelled. So that will we will get that identity is equal to beta. But again that is a contradiction because order of beta is 2 and identity element have order 1. So that is a problem. So that is not possible. Similarly, can alpha beta be equal to beta? We can write beta to be equal to identity times beta, which is equal to alpha beta, right? Again, we will use the right cancellation property, and then we will get that identity is equal to alpha, which is again a contradiction. Okay, so all these cases are not possible. So alpha beta is a different element. So identity element, alpha beta are all distinct elements. Now let's our ambition is to have this as a subgroup. So we should check if this forms a subgroup or not. Okay, so let's try to draw their table. Okay, so we will have identity alpha beta alpha beta. Again we will have identity alpha beta with alpha beta. Okay, now what is identity times identity? It is identity, then here alpha beta alpha beta. Similarly here also alpha beta alpha beta, right? Now what is alpha times alpha? It is going to be alpha square, which is identity. Okay, now what is alpha times beta? It is alpha beta. Now what is alpha times alpha beta? Here we'll have alpha times alpha beta. It is going to be equal to, by associativity, it is alpha times beta. What is alpha times alpha? It is alpha square times beta. What is alpha square? It is identity times beta, which is nothing but beta. So here we have beta. Okay. Now what is beta alpha? Beta alpha, we know that it commutes, right? Beta alpha is same as alpha beta. We have that alpha and beta, they commute. What does that mean? Alpha beta is equal to beta alpha, right? So here we will have beta alpha to be equal to same as alpha beta. Okay. Now beta times beta is beta square, which is identity. Now beta times alpha beta. What is beta times alpha beta? By uh, we can again use the commutativity here, and then we will get it is beta times beta alpha, which is equal to, by associativity, it is beta times beta times alpha, which is beta square times alpha, which is identity times alpha, which is alpha. So it is alpha. Okay. Now what is alpha beta times alpha? We are trying to fill this position, so we'll have alpha beta times alpha. Okay. Now by commutativity of this alpha and beta, we will have this to be equal to beta alpha times alpha. Now by associativity, it is beta times alpha. Okay. What is what associativity are we using here? We are using the associativity of the operation, which comes from the group. Okay. We know that the operation star, it comes from group, and in there alpha star, this star has to be associative, right? So that we are using. Okay. So it is equal to beta alpha square, which is nothing but beta. So here we have beta. Okay. Then next we have alpha beta times beta, which is nothing but alpha times beta beta, which is nothing but alpha. So we have alpha Then we have alpha beta times alpha beta, which is nothing but, by commutativity we have this to be beta alpha times alpha beta, which is nothing but beta times alpha times alpha using associativity, which is nothing but beta times identity times beta, which is nothing but identity. Okay, so it is identity. So from this we observe that this table, that the star, okay, this is a binary operation on H, that is H is closed under star. Okay, we observed that, right? Because in the table there are no other entries. We only have inside this table we only have identity alpha beta and alpha beta, right? There are no other elements, so H is closed under star. Okay, similarly every element have an inverse, right? Identity it's there, alpha its inverse is there, beta's inverse is there, and alpha beta is also self inverse, so every element have inverse. Okay, also identity element is there, associativity is there, so H satisfies all the conditions for it being a subgroup, so H is a subgroup. Okay, so we had started with a subset of G and we showed that it is a subgroup. Okay, now let's take a moment to appreciate the importance of both the conditions in the hypothesis. Okay, there are two conditions, right? At least two elements should be there of order 2, and then they must also commute. Why should it be? Okay, let's try to understand. So we will take a particular example to understand this case. Okay, so consider Z6. Okay, for those who know already know it, well and fine. For those who don't know, as of now, just take it as a statement. Later on, we will prove it. Okay, that Z6 does not have a subgroup of order 4. Okay, what are the elements of Z6? These are 0, 1, 2, 3, 4, 5. What are the corresponding orders? Identities order is 1. 1 has order 6. 2 has order 3. 3 has order 2. 4 has order 3, right? 4. 4 plus 4 is 8, which goes to 2. And then 4 plus 4 plus 4 is 12, which is a multiple of 6, so it is 0, right? Then we'll have 5, which goes to its order as 6. Okay, here there is only one element of order 2. Okay, so the hypothesis is not satisfied by Z6. So from that we don't get that Z6 has a subgroup of order 4. Moreover, using contrapositive, we can also say that since Z6 does not have a subgroup of order 4, it can have at most one element of order 2, which is true in this case. Okay, which we have seen here explicitly. Okay, now similarly, take D3. So here Z6, it satisfies commutativity. It does not satisfy the existence of elements of order 2, right? Consider D3. What are its elements? Its elements are rotation by 0 degree, rotation by 120 degree, rotation by 240 degree, and then we'll have various reflections, right? Mu1, mu2, mu3. Now here, mu1, mu2, mu3, all of them have order 2, right? Order of mu I is equal to 2 for I is equal to 1, 2, 3, right? But then D3 also does not have a subgroup of order 4. We will prove that later. Okay, this also does not have a subgroup of order 4. So what went wrong here? Here the existence is fine. So what should go wrong here? It is the commutativity. So let's verify this. If we write down the table just for this mu i's, we have mu1, mu2, mu3, mu1, mu2, mu3. So it will look like rho naught, rho 1, rho 2, rho 2, rho naught, rho 1, rho 1, rho 2, rho naught. Okay, and here we will have mu1 times mu2 is going to be equal to rho 1, and mu2 times mu1, it is going to be equal to mu2 times mu1 is going to be rho 2, which is not equal. Okay, so mu1 does not commute with mu2. Similarly, consider mu1, mu3. What is mu1, mu3? It is rho 2. And what is mu3, mu1? Mu3, mu1 is rho 1. Okay, which is not equal, right? So mu1 does not commute with mu3 as well. Now consider mu2, mu3. Okay, Mu2, mu3, it is going to be row 1. And what is mu3, mu2? Mu3, mu2 is row 2, which are not equal. So mu i's don't commute with each other. Okay, so the commutativity has a problem. So because of that, the hypothesis is not satisfied, and D3, from that we can say that D3 does not have a subgroup of order 4. I mean, the statement that we gave here is a sufficient condition. Okay, so that is we cannot say that since the commutativity is now there, and that much we cannot say. What we can say is, since it does not have a subgroup of order 4, there are two conditions, right? Either the commutativity must have been failing, or that we can say that there are no two elements, there is at most one element of order 2. Okay, so this is a powerful statement. If we have two conditions satisfied, that is, there are at least two elements of order 2, and both of them must be commuting. Okay, in that case, we can be sure that the group G has a subgroup of order 4. Okay, otherwise it need not have a subgroup of order 4. All right.